Okay, I am going to call this lecture A Graph Meets a Matrix, and you can see why on this picture I've recapitulated the fact that we've so far got this graph, nodes and edges, and we've been able to associate to it a matrix, which I called an incidence matrix. And in the first two lectures, I told you I actually just wrote down that incidence matrix, this very one, and told you a bunch of things about it that are true actually of any 5 by 4 matrix. I looked at the rank, I looked at right null space, I looked at left null space, things like that. And in the most recent lecture, I actually just told you some things about graphs. Here's a graph. I told you, for example, what a complete graph is. And the last thing I told you was a disconnected graph. Here's a question for you. Is this graph disconnected? Well, remember, disconnected means that there's a possibility that starting at one node in the graph, you cannot reach another node, some other node, by some path of edges. That's not true of this graph, is it? Because if I start at any nodes 1, 2, 3, or 4, I can get to the other nodes, any other one, by some path of edges. So this isn't disconnected. I'm going to, guess what, call it connected. Graph seems as good a word as any. Okay, so this is a connected graph. I can reach every other node from any given one through some path of edges. Okay, now I'm intrigued because I would like to know, what do all of those things that I know about the matrix A mean for this graph? You remember, I found, for example, this rather interesting vector, 4 vector. If I operate on that vector with this matrix A, that's what I'm calling this incidence matrix, I noticed that it was just 0 that I got as a result. Okay, and I called X a right null vector. Okay. Okay, it sits in the right null space of A. I don't know if you remember, but I also looked for solutions of this equation. And if you look back, if you don't remember, I found these two. I'm going to put them underneath me because I'll refer to them again later in this lecture. I found two linearly independent solutions, W1 and W2, to this equation here. This WTA is 0. I actually wrote another one down, W3, that just happened to be a linear combination of W1 and W2, so just out of interest. Okay, well, what does all this mean? Well, let's look at the right null space first. Let's do the following thing. Suppose I take, actually let me keep this on. Suppose I take some vector x. Okay, this is a vector x, and each element of this is going to be called a potential. I'm going to call it a potential at node I. Okay, it's a value that I assign to node I. And there's 4 of them because there's 4 nodes. Now I'm going to operate on it with A. And I don't know if you see, it won't take long for me to just work this out. Of course, I'm going to get a 5 vector. And if I'm correct me if I'm wrong, I get the following. I get x2 minus x1. I get x3 minus x2. I get x4 minus x1. I get x3 minus x4, don't I? And then I get x2 minus x4. Okay, let's just draw a little line there so it doesn't get confused. I've generated, from my vector of potentials, I'm going to call them, this vector. It's a 5-dimensional vector, and in fact, I'm going to call it E, because that's what I'm going to call it for the rest of the course. Okay, it's what I get when I operate on a general vector of potentials using A. Okay, now if you just had to say in words what E was, and it's that vector I've just worked out, what would you say? Well, I'm looking at it, and look at the first element. Suppose I've got my x2 value here and my x1 value here, then isn't x2 minus x1 just the potential difference across edge A of the potentials at the 2 nodes? It's x2 minus x1. Okay? Okay, so that's the first element of my E. And then can't you see also that if I look at edge B, x3 minus x2, which is the second component of E, is the potential difference between here and here. Okay? So in short, if I had to describe what this E was, I would call it a vector of potential differences. Okay? Interesting. So what does it mean then, with that interpretation, for me to look for a vector of potentials x for which the potential differences are all 0? Well, if the potential differences are all 0, that's what this says, it means that between any two nodes joined by an edge, the potential difference must be 0, which means the potentials must be the same. And this is a connected graph, which means that I can get from one node, any ones connected to that will have the same potential, because it's a 0 vector of potential differences, and then that's connected to every other node. So can you not see that for a connected graph, this vector x0, 1, 1, 1, 1, or by the way, any multiple of it, is the only right null vector for a connected graph. Okay? Because there's no way, because of its connected nature, that that AX, which is the vector of potential differences, can all be 0 without all of them being at the same potential. It just cannot happen. So that's interesting. My right null space of my incidence matrix is telling me that I can set my nodes all at the same potential and it won't change anything. Okay? Let's look at our W1 and W2 that are sitting beneath me. I'm staring at them now. There's two of these. And I want to somehow interpret those in my graph. I need 2 of something. So 2 is the magic word. What is it that there are 2 of here? Well, let me see. Well, node 1 and 3 have 2 edges coming out of them. Maybe that's important. But then again, 2 and 4 have 3 edges coming out of them. So maybe how many edges are coming out? Where else do I see 2? Well, there's 4 nodes, there's 5 edges. I've noticed something though. I've noticed it's got kind of 2 holes in it. Look, it's kind of got that hole and that hole. That's 2 of those, definitely. 2 and no more. And they're a kind of global property of the graph. I've got an idea. Why don't I imagine, let me construct a vector W with the following rule. Remember that here are my edges. So I'm going to construct a 5 vector. And what I'm going to do is, let me think about this loop here. If I go along an edge to make that loop, so in other words, I'm going to have to go along A, I'm going to have to go along C in the wrong direction to the arrow, and then along C in the wrong direction to the arrow. And I'm not going to go along B and D. You know, here's what I'm going to do to encode that activity. The first element, look, is edge A. And I go along edge A. So I'm going to put a +1 in there. My next step is to go along edge E, but I go in the wrong direction according to my arrow designation. So here's E. I'm going to put a -1 in there because I go against the grain. I go against what I set as the positive direction earlier on. And then finally, to complete this loop, I'm going to go along here. So let me just show you what loop I'm going. I go along the edge C, which corresponds to my middle row, and I'm going to go along that in the negative direction. And as for B and D, edges B and D, I don't go near those in this loop. Okay. Well, interesting, eh? let me use a green for this. Let me do the same for what's obviously this loop. Well, I go along B, edge B in the positive direction. I go along D in the negative direction. And I go along E in the positive direction. Do you notice anything? I've noticed that these two vectors are precisely the W1 and W2 that I wrote down in the first couple of lectures. Interesting. So, and I know that they are left null vectors. So I now have a geometrical interpretation of the left null space of this particular matrix. I don't know if it's possible. I'm intrigued to ask if there are other geometrical interpretations of left null spaces of other matrices. I don't know, but I certainly know that for this incidence matrix, it looks to me like I can associate loops, closed loops in my graph with the left null vectors. You remember I constructed a W3 as well. And actually I can see another loop in this graph. Perhaps it's not so easy to see, but look, why don't I just do this? There's another loop. I just don't go down E. That's another loop. And actually, if I work out what that is, you can see that it's what I called, well, I go down, let's just do it. Why not? We're here. 1, and then I go 1, and then it looks like I go down D with a -1, and then I go down C with a -1, and then I don't touch E. Well, guess what? That's precisely the sum of W1 and W2 that I saw earlier. It corresponds to this loop, but of course it does, look, because if I go around this loop, but kind of add this loop in, then I go this way and this way, which cancels out, so I don't go along there, and I end up just doing these 4 paths anyway. So W3 is geometrically W1 plus W2, because I go along E in one direction, but then I come back in the other direction when I add in my path from W2. Isn't it pretty? Isn't it pretty? We love it.